you a bit, my good friend, Dr. Bonney. So Dr. Bonney is originally from Iowa, so he did his PhD. Correct me if I'm wrong in some information. He completed master's and PhD in Wisconsin medicine, and then I don't think that he was very impressed with the US, and he moved to CA French Atomic Energy Commission. So, and I actually also moved from Cambridge after my PhD to French Atomic Energy Commission, and that's where we became friends. And before that, actually, he was working in Sandia National Lab and others. And now he's working in a big consortium of universities and industries on digital twin projects for dynamic systems. And now he's in University of Sheffield, but he's moving to his new position as a professor at University of Swansea in Wales. But he's actually my collaborator in projects, and I'm working towards DigiTwin and all. He will be also going to be our collaborator for so long. That's what I'm expecting. So I'm actually giving the floor to Matt. So Matt, if I'm missing information, obviously you can fill it up. Thanks, Matt.
All right, thank you, Dr. Long. So I said I'm Matt Bonney. I guess I finished about 6 years ago with my PhD. So it's been a while, been in Europe. So it's nice to come back to the America University. Not quite what I remember being on the other side of the student compared to professor level, but interesting nonetheless. So I've been doing digital twin research for the past 3 years or so, specifically about digital twins, and mainly focusing around multidisciplinary aspects, whether that's a mixture of engineering, mechanical, civil, aerospace, or whether it's business, computer science, engineering, manufacturing, everything around that I've been dealing with that for the past 3 years or so. So my main talk today is going to be around the general concept of digital twins, why I found them interesting for the past couple of years, some of the history and how they can be applied to a lot of different systems, and why it's such a buzzword now, but what it actually can represent. So first, I'm going to start with a historical perspective. How did digital twins come to be? Why they came to be? Things like that. Talking about what digital twins are and why asking that question is not a good idea in most contexts, which is a very interesting concept for most people. Talk about what digital twins are compared to what the enabling technologies are, and then talk about claims and what people are selling as digital twins, whether that's in natural industry or in research or in open source. Then I'll end up with doing a little bit of publicity for my own work, as most of these seminars always do. So I'll end up with that. So first, when you think about digital twins, the main idea comes from twins. So twinning. And this, most people take this back to the Apollo missions back in the 60s and the 70s. And the initial idea came up to be of, well, we're going to need to train these astronauts in order to actually operate in space. So what they did was they built the operation or the command module twice, one to set up space, one for training. And then, as you know, the Apollo missions didn't go according to plan. So when things started happening, they came up with the idea that, well, we have this exact command module that they will be using. So let's test that out and see what ways we can manipulate it so that we can get our astronauts home safe. So that's where the idea of twinning kind of came in. The idea of a digital twin was kind of accredited back to 2002 by Dr. Greaves. And the actual idea was project lifecycle management. So a way of maintaining the lifespan of the system and being able to actually project it and understand the life of the system to better operate it as an asset manager. And in the initial publications, they weren't called digital twins. They were called virtual space representations. If you heard anyone talk about digital twins, that's kind of what it is, the virtual representation of a physical system. The idea of a digital twin, or the term digital twin, kind of first came up in 2010 via NASA roadmap by Dr. Vickers. So when people talk about the origins of digital twin, it's always Greaves and Vickers are the two main people in the initial generation of digital twins. And so since 2010, one of the biggest questions have been around what are digital twins? The concept is fairly ambiguous. Is this a virtual representation? What does that mean? How rigorous is it? And it's also expanded about how is it different from our current techniques? We've had calibrated models for decades. We've had IoT solutions for decades. How is a digital twin different from all of these current situations? So what are digital twins? Well, the actual definition is very much highly under debate. So whether you talk to a computer scientist, a mechanical engineer, an aerospace engineer, a manufacturing engineer, they will have different definitions for what a digital twin is. And particularly if you go to things like the Air Force, the DoD, they want to put definitions on before they do anything. But several industries have started putting forth their own definitions. One example I like is the manufacturing digital twin. So it's an ISO standard now, 23247, and it a fit for purpose digital representation of an observable manufactured element with synchronization between the element and its digital representation. So that is a fairly broad definition, but also very specific at the same time, because it talks about specifically observable elements, and it talks about synchronization between the digital and the physical systems. But as you look through the definitions, I think I saw a paper the other day that said there are 57 different definitions of digital twins in journals right now. So a lot of different definitions. If you kind of go through and read them all, there's kind of some key components that people like to represent. So one of the main key parts is that there's a pairing between the physical and digital systems. So there needs to be some type of synchronization, whether that's a calibration every month, every day, every hour, whatever it is, or if it's a live feed of data that goes into the model. How it's actually implemented is up for debate, but there's the general idea is there had to be some pairing between the physical and the digital systems. Second, a digital twin is more than just a calibrated model, particularly if you look at aerospace, where they've had calibrated models since the beginning of the computer. And so they've taken data, they've made their models fit that data, and they use that to make future predictions. Very common in aerospace situations. But the digital twin is more than that because it evolves with the system. As the system degrades over time, the digital twin must degrade over time in terms of actual material, not in complexity or anything like that, but it needs to evolve with the system itself because nothing stays exactly the same ever. And the last part that a lot of people do, this one's a little bit more under debate, is that a digital twin comprises of predictive modeling, visualization of data, as well as data collection and storage. So in the way that I like to phrase this, it looks at the past through the data collection, data storage, looks at the present through the visualization of the system, and it looks at the future with predictive modeling. So when I consider digital twin, those are kind of the three main components I think about. So here is a picture from the roadmap from NASA back in 2010 with the original definition of a digital twin. So when they originally put it out, they had four kind of key components of a digital twin. I'm currently saying three, but some it kind of works out. So the first part is high fidelity modeling and simulation development, which is what you expect. You want to be able to make predictions. You want to be able to have accurate models of your system. Otherwise, you can't really have a pairing between the physical and the digital systems. The second, which is something that I feel that a lot of people are kind of leaving out currently, is design and certification methods. Aircraft need to be certified to fly. They need to go through the FAA. Nuclear reactors need to go through safety analysis and reports and things like that. The digital twin should have this according to the original definition. So whether that is inspection reports, certification, probabilistic design, all kind of within the digital twin itself. Life prediction sustainability, so be able to predict how the system will evolve throughout time. Things like remaining useful life, predictive maintenance, things like that. And lastly, situational awareness. So this is kind of the more live aspect of if there's a bird impact on an aircraft, can we predict how that will happen? Or if it does happen, how do we react to it automatically rather than waiting for the pilot to respond? If a nuclear reactor goes off, you want to make sure you shut that down as fast as possible. So being able to implement that type of stuff into the digital twin as an automated safeguard is really useful. So that's kind of the initial definition, what is within a digital twin. Now, the main question that people should ask when asking about digital twin is, what does the digital twin do? I feel that's much more pertinent and much more reasonable question to ask rather than what is a digital twin, is what does the digital twin do? And my cheeky answer is always what it needs to do. A software does what it's programmed to do. So if you think of the digital twin as a software, you program it to do something and it does it. How complicated that becomes is very particular in terms of the programming, but it does what it needs to do. And so in my vision of a digital twin, which has been a combination of a bunch of different industries, a bunch of different disciplines, the main thing that I feel that digital twin needs to do is it needs to operate in the past, the present, and the future. If you look online, if you look for what people call digital twins, some only look in the future with predictive modeling. Some only look at the past, particularly with civil engineering structures, where they care about what happened over the past 24 hours or whatever. Or some just look purely in the present, such as manufacturing, where you have the VR headsets that have really cool visuals, but that only is looking at the current. It doesn't make predictions in the future. It doesn't look into the past. So within the digital twin, I feel it has several components that relate the user to the physical system itself and all the data associated with the digital twin. So the digital twin should have some tracking or data recording to investigate how the system has evolved throughout time. When you talk about reactors, you talk about aerospace systems, they have very long lifespans, 20, 30, 50 years. In order to get a better idea on how that will degrade in the future, it's very important to know how it has degraded in the past. So you can infer information from the past data, or even transfer the information from one reactor to the next reactor. So you can learn something from your asset rather than just having everything be ad hoc. It needs to have some type of monitoring or some type of visualization of the data. And that's to identify the current state of the system. Understanding that the people that are going to use a digital twin are people. You need to have some type of visualization. You need to be able to represent the data rather than just a list of numbers. It needs to be a 3D model with a particular point of, oh, we're expecting a crack here. Or it's something along the lines of, here's our predicted end of life in an English sentence, or whatever language you want to put it into. Having some type of visualization, some type of monitoring aspect with sensors, with visual, or with whether that's physical sensors being attached, accelerometers, temperature probes, things like that, or inferred knowledge through reports or through inspections, things like that. There needs to be some type of monitoring aspect of the digital twin. And as I said, it also needs to predict the future. And so, since the system is evolving throughout time, particularly in the small or the slow timescales, being able to predict how it's going to evolve throughout time. We also need to make predictions such as earthquake reliability. If an earthquake happens, particularly one that we haven't seen before, like a Fukushima, of course, we want to be able to predict how to respond to that and be able to predict what will happen to the system, how to safely mitigate that issue. And of course, last but not least, is there needs to be some type of physical connection or some type of connection to the physical system. Whether that is physical through sensors, things like that, wires hooking up, maybe Wi-Fi, 5G, whatever you want to use. Or if it's collected data sets that you use to calibrate the models to do everything else. So that's what a digital twin does. The next kind of question is, how does a digital twin do that? And so they do it through what I've been calling the digital twin enabling technologies. So these are the components of the digital twin that are needed in order to perform the actions asked of the digital twin. And so the way to kind of distinguish this in your mind, which really helped, particularly with my students, is a digital twin is a single product for a singular system. The enabling technologies is transferable knowledge from one system to the other. So if you think of finite element modeling, that is an enabling technology. In order to have accurate predictions, with particularly structural components, which is what I deal with, you need to have some type of representation of the physics of the system. And so that's typically done through finite elements. If you develop new technology in finite elements, that's not helping one system, that's helping many systems. But if you're looking at a digital twin of a system, that is very specific to that singular system. Because of this, when you start looking at enabling technologies, they tend to be very singular disciplinary in nature. Finite elements are primarily mechanical based. Computational fluid dynamics, different type of mechanical base. Chemistry, manufacturing, all that stuff tend to be singular disciplinary focused. While the digital twin itself needs to be multidisciplinary. You can't have an asset without knowing how much it costs in dollars to run that asset, to make predictions on how much it will cost to repair the system that is multidisciplinary in nature. So when you actually look at digital twin research, what tends to happen, from what I found, is that most digital twin research is about an enabling technology. So I'm going to give me $1 million in order to study this one particular aspect of the digital twin because I'm a singular person working on a singular discipline. So that tends to be around digital twin enabling technologies. And very few people focus on the digital twin as a whole, because that requires multidisciplinary approach, that requires a consortium of information of varied people with varied industries. It's very hard to set up one of those types of things. So when you think about research on digital twin, most of the time, whenever you read it, it's going to be an enabling technology. So, as most of you, since you're here, probably have heard digital twins before, and most people have a lot of claims around digital twins. So one of the common claims is that there's a reduction in what's called lost time. And so this is the time associated with logistics, with bureaucracy. So if the CEO wants to ask a question about the system, how much will it cost to run my system one more year? What typically you have to do is that CEO would have to ask the business manager, would have to ask the lead engineer, which would have to ask the technician, and everything has to get filed back up. That takes time. People are on vacation. People are off on the weekends, unless you're in academia, of course. But all that takes time. And so that the use of a digital twin, what that would allow is the CEO to enter a centralized platform that it will go and do all the simulations kind of automatically and report back to him the information that he needs to make that decision. And so there's a large amount of lost time that is gained up by using a digital twin. That should be too close, whatever. One of the other things is reduce operational costs. So that's one of the main common claims that use a digital twin, you can reduce your operating cost by 30% or some number that they pick out of the air because no one's really done it yet. So it's kind of hard to put an actual value to it. And so a lot of this comes down to things like optimal maintenance. I deal a lot with offshore wind turbines, not popular here in the US, but very popular in the UK. And in order to do repair on the offshore wind turbine, you need to take people out on the boat, take the boat out to the actual system itself, rig it up, and actually do the repair itself. That costs over £1 million a day to do that repair. And you have to worry about things like weather. You can't go if the seas are too rough. You can't do it at night. Can't do it in high demand because you waste a lot of time. So implementing something like a digital twin really helps kind of identify okay, go look at the meteorological information. What is the sea going to look like tomorrow? Well, this could be bad. Okay, what about on Monday? How's that going to look? And figure out if you can still do the repair within that time frame without costing way too much money. Or if we know we can run the system for another month before repairs, let's push that back as far as we can, but still safely with the weather conditions and things like that. It's also commonly associated with optimal performance. So if we have a reactor and we reduce down the output by 10%, and if we can prove with the digital twin that that would save us 20% of fuel costs, that might be worth it. That might be the optimal amount compared to the supply, demand, and also cost. And so most people, when they think about digital twins, also think about that aspect of optimal operations. Of course, that requires a lot of information on the technologies, but that's what a lot of people associate with digital twins. And last is reduced design time. So one of the common ones is NVIDIA Omniverse. So NVIDIA, the graphics card company, they have their own Omniverse, metaverse, what do you want to call it, based around novel designs. The idea is that if you come up with a design of, say, an aircraft engine, you can put it onto the GPU accelerated platform of the Omniverse, perform whatever simulations you need to do to see if it passes any criteria that you have. Whether that's structural in terms of vibrational characteristics, whether that's a weight criteria, anything like that, you can kind of program up and use the NVIDIA Omniverse. GPU powered, so it's fairly fast and efficient in computational time. What you can also do with that is if you make a small change, say, reduce the thickness from 5 millimeters to 4 millimeters, you can easily send that back to the Omniverse and get the results back. So this is typically around the association of what's called a design digital twin, where you're designing within a digital twin for a system that doesn't quite exist. So when you talk about design digital twins, it's very debatable aspect of whether or not that's an actual digital twin or whether that's just a model. So particularly when you talk to computer scientists, they consider that just to be a model. They don't consider that to be a digital twin at that point. Talk to design engineers, that's a digital twin because that's an easy way of getting money. It's calling what you're already doing a digital twin. So those are kind of some of the common claims around what a digital twin is and what it can do. So as I kind of mentioned before, there's kind of multiple ways about thinking about digital twins. So one of the first things I did when I started learning about digital twins is I kind of looked through the literature and kind of came up with some categorizations of digital twins. So depending on who you ask, sometimes there's 4, sometimes there's 3, but typically there's about 3 main types of digital twins. And it's primarily based on the scale or the outcomes desired of the digital twin itself. So the first is a product or part-specific digital twin. So this is kind of the more historical definition of a digital twin. So this is a singular system or components, and it focuses on the design or the structural health of the system. So this is things like a singular aircraft. It has a tail number of XY1246. It relates to all the different flights it's had throughout its life, any repairs it's had. The exact model, any manufacturing defects are all incorporated into the actual product specific digital twin. The second one is a process digital twin. And so this is typically associated with the Internet of Things or IoT. So these are common things like manufacturing. I've seen several that are welding robot based where there needs to be a human in the loop effect where a person needs to hand the welding robot a sheet of metal, and then the robot's going to weld that, and then the human takes that sheet and moves it to the next part. And so what the user will do is they put on a AR headset and interact with the machine as normal. But because he's wearing the headset, that gives information back to the robot itself. So the digital twin of the robot can see where the human is to make sure that it doesn't whack him in the face and knock him out. Simple safety stuff like that. But it can also be used for things like chemical operations. I've seen a digital twin of a shampoo filler plant, whatever you want to call that. So you can monitor things like chemical reactions, you can measure things like filling up a bottle full of shampoo, things like that. Or even things like energy transfer within a reactor. And last, but certainly not least, is what I call infrastructure digital twins. So these are much larger in scale. And so they tend to have multiple systems within it. So things like the electrical grid, things like a supply chain, things like London. There's many people that have a digital twin of a city, whether that's a big city, whether that's a small city. These are typically infrastructure digital twins. And they even relate to things like a fleet of aircraft. If you think about like Virgin Atlantic, they have so many aircraft with particular tail numbers. They can have an infrastructure digital twin that looks at each system individually. So you think of it as a wrapper around all these other part-specific digital twins. So those are kind of some of the broad categories that digital twins could be applied to. When you start looking at actual digital twins, what you'll see is a lot of people are selling digital twins. And so there are way too many proprietary digital twins to list. Last time I saw, there's north of a couple hundred at least. So I found this good visualization by a company called Quasar that is selling digital twins, of course. So digital twins kind of fall into two main specialties. It can either relate down to machine learning, so things like AI, other machine learning techniques, or it can be simulation. So finite elements, computational fluid dynamics, things like that. And so the reason for this is because there is no formal definition. Because there is no definition, it's really hard to kind of specify here is the type of digital twin it can be. So we have these up here, which is what we call mainly computer science focused. So they're doing machine learning, they're doing AI stuff. So things like AWS TwinMaker, which is the Amazon cloud service, the Azure, which is the Microsoft cloud service, they're digital twins. All it does is it takes data, makes a model that using machine learning, it comes out with a prediction. So that's more of the computer science, machine learning aspects of digital twins. While there's others that are purely based in simulation, such as ANSYS TwinMaker, which allows you to take a finite element model and create a virtual sensor and tie that to a physical sensor to see how well those two match up. That is what the ANSYS TwinMaker does. And that's purely based on the finite element analysis and a little bit of IoT. You also have what's called Siemens executable digital twins, which are a very interesting aspect that I'll show you a little bit more about. So this is a promotional video by Siemens. I've edited it down because it's 10 minutes long, so I just took out the minutes I want. But this is a demonstration of what they call their executable digital twins. What the executable digital twin does is it takes live data and maps that onto the finite element model to provide like things like stress distribution of the system. So that's live. I don't know if people online can hear that or not, but we kind of see we have a digital twin of the system on the iPad that's mapping the real world system onto the digital system. So it's using things like computer vision to identify where the robot is, where the actual physical system is, and it's doing on-the-fly computations through a surrogate model. So if I know that I'm going to have some type of pressure being applied to the top of the plate, what it does is it sees and records what the actual pressure is and performs the quick finite element simulation to figure out what the stress distribution is. So you can see there's high stresses here. We can see some stress on the legs of the system. And we kind of go through and identify through a live video where your maximum stress can be and where things like propagation can happen. So that is a Siemens executable digital twin. And so that's mainly looking at current state and future state, primarily in the current state, actually. TwinView is another proprietary company that's selling digital twins, but they're mainly focused on the past. But they have a weird, interesting thing where they're using a browser-based interface to interact with data for a building information model or BIM. Much more elaborate. But what they have is a web interface. So the owner of the building can go online and access what the system's doing. Whether that's environmental conditions through sensors, what the HVAC system is doing, and even things like energy costs. You can incorporate the actual cost of energy into the system. Wait for the meeting to die down. What's interesting is on the right here, you see the information, the metadata associated with the system itself. So you can go in and see, I have one water boiler. I can go in and cook on it and get the metadata information of when was it installed, when was it last repaired, what is its current state, what's its power input, what's its flow output like. You can get all the information in real time or look at what has previously happened with stored data. And you're able to go through a visualization of the full building and investigate singular components. So it's a very interesting aspect. I particularly like the browser-based aspect of that, because that relates back to some of my own research. But you can either go to it on a computer or even your phone, so that the building owner can be anywhere in the world and see what his system is doing. So those are some examples of some proprietary digital twins that would cost money in order to actually use. Alternative to that are what's called open source digital twins. So if you think of things like Linux and things like that, that's the open source comparison to Windows or Mac. So you see there's a big fight kind of in the world about open source versus closed source or black box, however you want to call it. And when you look at open source digital twins, there's very few to actually specifically talk about. One of the big ones is called DTOP, which is an IoT-based platform that does what is called data pipelines. So it's good at connecting proprietary hardware, whether that's accelerometers, temperature gauges, pressure gauges, whatever it wants, into a centralized system for an analysis to do. Because if you look at things like accelerometers, they're not going to be the same manufacturers as they are temperature probes in a lot of cases. And dealing with their individual software is going to be very difficult to do because it's a proprietary software to begin with. So DTOP has kind of worked its way around as an open source IoT platform to connect all these different proprietary sources to a singular source, whether that's in Python, whether that's in C, whether it's in some common language. But it's able to connect everything together and do some automated processing of the system. There's another one called iTwin.js or JavaScript, and it's a web-based application for infrastructure. So it's very similar to the TwinView idea I just showed you, where you go online to visualize the system and to gain information about the asset itself. So with TwinView, it visualizes the data and interacts with live sensors. So the iTwin is very interesting with TwinView because they're essentially the same results, but one's proprietary, one's open source. So if you had a building and want to get a digital twin of that, you have these multiple options to kind of vary. And so a lot of the idea is that what you're going to choose is based on who you trust. Do you trust this proprietary company that you can get some type of warranty, some type of accountability for? Or do you trust the open source software where you know exactly what's happening with the data? You know the analysis is going, you know where it's stored, you know everything about it. which one do you trust more? Which one costs more? And is that cost worth the trust? So that's some of the interesting aspects around open source digital twins that not many people consider because they don't need to worry about selling open source digital twins. They don't need to worry about differences between different types of digital twins. And lastly, is my own research, what we call the Digital Twin Operational Platform Framework, or DTOP Framework. And so the way that we kind of built it around was transparent data manipulation based on interconnectivity and accessibility. So first, make sure I'm not running too much out of time. Good. So now I'm switching over to the advertisement part of it, of my own research to get some work in there. So the DTOP framework is what we've been using in order to generate digital twins. And so the way we've developed it is multiple layers approach, which allows a separation of work. It's primarily browser-based, but doesn't need to be. So we can think about things like web design. I'm not a web designer, but I can hire someone to make HTML for me. And that will make my product so much better so that engineers don't have to do everything. We can leave experts to do what they're experts in. So the DTOP, or Digital Operation Platform, kind of consists of three main layers. The top is the computational layer. So this is where the database is of all your data information. This is where your simulations are. This is where you connect to cloud computing or to a high performance computer. All that connectivity happens in this computational layer. The middle layer is the interface layer, and this is how the user actually interacts with the system. Many people talk about the general idea of digital twins, but very few people talk about how a user actually interacts with the digital twin. Is it through a browser? Is it through an executable? Is it through a VR headset? That's something to consider, particularly when you're making a product. So this is all done within the interface layer. And you also look at things like, do I need to be physically next to the system in order to operate the digital twin? Sometimes you do, sometimes you don't. And lastly, is the Internet of Things layer that is relating the digital twin back to the physical twin. So this is things like sensor readings, making sure you set up a sensor network, as well as bidirectional controllers. A lot of digital twins want to actually influence the physical twin. If you want to do automatic avoidance of incidents, you can have to use some type of interaction between the digital into the physical, not just the one way from physical to digital. So that's all in the IoT layer. And honestly, this is the area we've least developed because we're doing open source. You don't want to give open source to a physical system. If we put in actuators onto an aircraft that we have, someone online is going to go up there and start shaking it to some extreme level and break our system. So from an open source perspective, this is kind of where we're lacking, but it's something we're working on with open source Raspberry Pi based sensors. So doing some interesting things that way, but those are kind of the three main layers, and it's all tied together through this connectivity network. So connectivity network can be in person or physically connected together with wires. It can be through a Wi-Fi, through a LAN, or it can be on the open internet with 5G or whatever else needs. So one of the key things that we found when we were looking at creating digital twins was that very few people worry about the interface layer. So what we've done is we've developed multiple deployments of the interface layer based on what the actual system itself needs. So the way to kind of think about it is the digital twin is a server, and you're going to SSH or remote desktop into the server in order to operate it. So we've figured out three main deployments. The first one is the standalone deployment. And this is kind of the most secure because only one person can operate the digital twin at a time. And so we've demonstrated this with one of our demonstrators called DTOP-Cristallo, so that you can run the digital twin on your laptop, on your computer, and you have access to that. No one else has access to that. So this would be good for things like reactors, energy producing plants, things like that. The second allows it to a local network. So particularly in things like aircrafts, reactors, not just one person is going to be interacting with the system at a time. You're going to have a team of people interacting with the system at a time. So since you have a team, they need to be able to access the information. So that's why we developed the local area network deployment. So whether that anyone on a physical asset or on the physical premises can access the system. And so we demonstrated this with DTOP-DTHIVE, which is a fighter jet that we have in our lab. And lastly, we have the web page, which anyone that has internet access can access the digital twin. Whether that's on a computer, whether it's on a phone, doesn't matter. As long as you have internet access, you can access the digital. And as you would expect, this is very insecure. So this is the type of deployment that you need to insert your own cybersecurity into, whether that's things like username and password, whether that's IP identification, authentication, whatever you need to do. But in terms of upfront costs in order to deploy, you need to implement a lot more cybersecurity in this web-based deployment. So I'll talk about different demonstrators. Our first demonstrator is DTOP-Cristallo, which is named after an Italian dolomite. We had 4 main people developing DTOP-Cristallo, myself, a climber, and 2 Italians. So I kind of got overruled in naming conventions. So the dolomites are just a mountain range in Italy. So DTOP-Cristallo is our first demonstrator of the DTOP framework of this scaled 3-story structure here. So it's something that we have in our lab. It's on a bench top that we can do whatever we want to it. It's fairly simple. It's made purely of aluminum, I almost said aluminium. And it's very simple to manufacture, very simple to manipulate, very simple to predict. So we figured this was a really good demonstrator in order to do that. So this is publicly available on GitHub. If you want to look at QR code, that will get you to our GitHub page, or you can just kind of search for it. And in there, there's also a YouTube video on how to download and run DTOP-Cristallo on your own computer. And so it's here, and it's also in the documentation in the GitHub. So this was developed as part of the EPSRC Digital Twins for Improved Dynamic Design, which is the program grant that I'm part of. It's a consortium of 6 universities. So in DTOP-Cristallo, we have 9 modules made from 6 different programmers at 6 different universities. So we're very proud of the multiple people input type of thing. And the basic of it is that it's using Python as its programming language. So all the computations are done in Python. And it's using HTML and JavaScript as the interface. So it's a browser-based digital tool. So here's what the main page of DTOP-Cristallo looks like. It's a website. You click on a link, you go to a module, you do an analysis. So I can do a numerical simulator. I can put in a finite element, a 3-degree of freedom system, and I can simulate the time history. And that gives me a time history, and I can do whatever I need to. I can do things like uncertainty propagation. If I have uncertainty bounds on my, say, stiffness or my mass, I could propagate that into the frequency response. So you can do a bunch of stuff. So this is a video a student of mine made. Luckily, this one doesn't have a bunch of sound going on. And this is our initial attempt at doing IoT and actual physical connection to the system. So what we have here is our 3-degree freedom system. It's hooked up with 6 accelerometers, and we're going to impact it with a hammer in order to create dynamic motion. So if you don't know much about structural dynamics, don't worry, it's not a big part, but we're doing a simple impact test. So what we have here is we have the computer in the back that's physically connected to the hardware. So it's connected to the data acquisition that's connected physically to the system. And so what we can do in the DTOP is, if click start, we're actually telling the data acquisition to start collecting data. And so it gathers that data and displays it to the screen. What we can also do is, because it's going to land deployment in this case, we can do the exact same thing on our phone that has no physical connection to the system at all. So if I want to, say, gather information remotely, we can do it with our DTOP-based system. So in addition to just gathering data, we can also store that to database. So we can retrieve that data at any time that we want, as well as download it in something like a CSV or some simplified format that we can use for other further analysis. And so we can see that this is the exact same data on the phone and on the computer. And because we're using a browser, we're using JavaScript, that makes the plots dynamic. So we can pan, we can zoom, we can adjust whatever axes we want to do, and we can actually manipulate the data that way. In addition to just visualizing the data, we can also perform analysis with the data. So what we're doing here is a simple what's called circle fitting routine. So we're getting some dynamic characteristics out of the system. And we're able to take that data, do the analysis, and report that back to the user. And we can do that both locally on the machine, or we can do it on our phone. And one of the cool things is when it's on the phone, your phone is not doing the computation, the server is. So that you can do it on any lightweight device. And so you don't have to worry about, okay, I'm going to do this on my phone, and then I can't use my phone for an hour. It's all done on the server base, on the server side. So that's our simple demonstrator, a very academic lab system. Since then, we've come into a fighter jet. We have a big lab at Sheffield called the Laboratory for Verification and Validation, where we have a fighter jet in there. We also have a full helicopter in there. And so we have these fully available to us. We can do whatever testing you want to do on that. So we decided to use one to create a digital twin of one of these systems. So we've chosen the fighter jets. For those in aerospace, it's the BA T-1A Hawk. So this is the same fighter jet that the UK equivalent of the Blue Angels used for things like parades and for like the Queen's Jubilee that happened last summer. There's a lot of Hawks flying in the air for that. It's typically it can go supersonic. It's mainly used for training new pilots. So to take a full system, we decided to try to demonstrate an actual industrial-based server deployment, where we attach a formal database to that, and we're making the data set that we've collected publicly available. So if you're interested in doing some type of structural analysis on an aircraft, that data set will be available for you. And so here's what the front page of that looks like. You can tell it's very similar because we're not website designers, so we didn't want to make it too bespoke. So we kind of copy pasted a lot of stuff over. But we can see we're doing very different things, where we can look at things like the finite element model. We can look at things like the database data itself. We can gather that, we can upload data all through this web platform. So here's how you do a finite element analysis on the web. So this is our finite element model of our Hawk system, primarily the shell-based model of it. And essentially all we can do is on the left side is you can put in the material properties, you can put in the analysis properties, you can put in the mesh seed. And then you can either run it correctly on Abacus, which is calls Abacus and does the analysis, or you can save the Python script for later. If you want to say change a couple things, whether that's a different analysis, things like that, you can save that to a local file and do whatever manipulations you need to do. So as I'm getting closer on time, yeah, just about perfect. Digital twin is kind of a very fuzzy understanding, and particularly because there's no formal definition. It's kind of hard to say a digital twin of this is the same as a digital twin of this, particularly because the industrial use cases are very different. And it dates back to the Apollo missions back in the 60s and 70s, with the digital aspect of that really coming together in the early 2010s. When you think about digital twins, it's very important to kind of separate the digital twin itself as a product, as a software, to the enabling technologies that are implemented inside of that. That's very good for research-based stuff. When you look online, you'll see a lot of people selling what they call digital twins. Be very wary in case you're ever buying a digital twin or whatever, which I doubt a lot of people will, but people selling this as if it's snake oil. So be very cautious about how you talk about digital twins and how you represent digital twins in any research that you do. So we have either proprietary, which through these people selling it, or we have open source solutions for creating these digital twins. And particularly our DTOP framework is open source, it's accessible, so most people can access it remotely, whether or locally, and connected to databases, to distributed computing, to multiple people, all through this digital twin operational platform. And if you're interested, DTOP-Cristallo is publicly available through GitHub. So with that, I answer some questions now. If I don't get to it, feel free to email me as well.
Matt, yeah, learned a lot, but we have been discussing about that for quite a long time. And so the thing is that actually when I was writing my proposal on digital twin or writing papers, actually I always talk to him so that I'm not doing this false claim you mentioned. Yeah, so I just want to check with you. Yeah. So any question for Matt? Like
yes. So I have a question about the database. I mean, data connectivity with physical access to digital twin access.
Yep.
So in that case, if we consider the digital twin for nuclear system, there are over 100 or several hundred physical centers will be there.
Yep.
So in that case, how do we prepare database? Actually, I have no idea about database. So each service, there are several services, right?
Yeah, so it depends on how you want to set that up. So as a general idea, the idea of big data is very important for a lot of people because, yeah, as you said, Reactors have a lot of sensors. They live for very very long time, so that can accumulate a lot of data. So it comes to now a philosophical debate. Do you keep everything and maybe be useful? Maybe you keep as little as possible and only figure out the relevant stuff. That's kind of the real question. The way that I like to go about it is I do a rotary buffer. So store only the last, say, 10 minutes of data or whatever. And then once something happens, some trigger happens, whether that's a human clicking, I record the data, whether we see a large stress, large strain, something like that, and then dump that to a permanent database for investigation later. So it's really kind of up for debate and kind of relevancy for your system. Yeah, reactors have a lot of systems, a lot of sensors. Some of the other systems might not. If you think about a building system, they might just have one temperature sensor in each room. And so that's not a lot of sensors for most systems. And so maybe you can just store that permanently.
Yeah, one thing before that, actually, the first one question I want to mention that. So looking at very cool video, don't get demotivated. That always it's a very difficult problem. He has 6 employees under him, like really trained computer scientists, like finite element experts and all. So he's leading a big group. So it's actually like a consortium type of thing. So I just want to mention that if you feel like, okay, I want to do that, but it's lots of work. Can I do that? It's actually lots of people are working on that. I just wanted to make it clear so that they feel like, okay, yeah, it's really like, I cannot do that.
Yeah, that's kind of why a lot of people are researching the enabling technologies, because that's single disciplinary. That's a lot easier to chew. Like, okay, I can solve this one particular problem. Studying full digital twins, as I said, requires a lot of people around you. So whether that's the multiple people in our DTOP framework development, or whether it's my current employees, whether they're computer scientists, mechanical engineers, aerospace engineers, whatever they are, it takes a lot of people.
Yeah, sort of.
You talked about synchronizing the physical system and the digital system.
Mhm.
Is it both ways, or you only synchronize through physical to digital, but not backwards?
So typically it's only physical to digital because the digital system doesn't have natural degradation. The system itself can't devolve at start time, minus things like bit rot and other things like that. But the physical system is a more dynamic system where it's going to change throughout time, while the digital system is kind of the snapshot version of that. There are situations where, say for like an aircraft, if you have a digital twin of an aircraft, and you're telling the digital twin to activate the flaps on the wing, then essentially there's the feedback from the digital system into the physical system that's updating the physical system to represent the digital system. But in most cases, it's typically one direction from the physical to the digital.
When both ways are possible.
Yeah. You need specialized equipment, actuators, and bunch of things like that, but it is possible.
I see this is a user interface for FEA, right?
Mhm.
So, okay, so when you click submit, how long will it take?
So it depends on the analysis. For that particular analysis, about 90 seconds, 2 minutes.
90 for what? For temperature or stress?
This is just eigenvalue analysis.
Oh, just I don't have.
But you can do whatever analysis. Essentially what that run button does is it goes to command prompt and tells Abacus to run this analysis. So however long it would take to run an Abacus, it takes the same amount of time here.
And do you think simulation time is a challenge for digital twin? Because in our lab, when we run some thermal simulation, one simulation would take maybe 3 to 4 hours.
Yeah.
And as I know, in digital twin, it is very emphasized real time or simultaneous. So what do you think? Is
Yeah,
that-
so in my mind, it depends on what you want that simulation to do. Do you want the live time thing, which a lot of things are very important on that? Then you need to create some surrogate model that acts in near real time. But there's also a lot of people that want to use the full finite element analysis because it gives you so much information. And so something like the operational platform, we can connect that to a high performance computer or put it to a distributed network of, I can send it to some remote machine to run. 3 hours later, I'll get an email saying it's done. So we can distribute it that way. So in my mind, that's not a challenge of digital twins. It's a challenge of the simulation technology.
Yeah, by the way, Freddie is from mechanical and aerospace. So he's actually working on both experimental and simulation aspect of digital twin.
Wow. I have a question relating to previous
Yeah.
question. How about replacing the abacus simulation with surrogate model created by machine learning?
So using Abacus to create the data using the machine learning model.
Yes, yes.
Yeah, that's entirely possible. I've seen a couple systems do something very similar to that. We have this high fidelity model that takes forever to run. We want to use that to create some physical information about our system. And then we're going to take that and we're going to take some experimental data as well, merge that together through machine learning, whether that's a pin or whether that's anything else, and use that in more of the real-time simulation aspect. So visualizing something like the executable digital twin from Siemens, that uses surrogate modeling. It does full finite element analysis with and creates reduced order models based on input location. And it creates a set of these. So when it sees this particular point as being excited, it goes to that reduced order model and actually calculate what the rest of the system is going to be. So that uses the full finite element model to inform the surrogate model that uses real-time analysis. So as an example of it.
Yeah,